In this video, I'm going to talk about the Miliken oil drop experiment. Just not going to go into detail on the experiment specifically, but just more of an overview. The idea here was that Miliken was doing an experiment to determine very small electric charges. So this isn't really reflective what the apparatus he actually used looked like, but basically the idea for our purposes is that he had a set of parallel plates. Those parallel plates were attached to some sort of battery. And then there were tiny oil droplets that he had, and those oil droplets were charged. So if let's just say for the sake of argument they were charged to be negative, then the positive plate was on top and the negative plate was underneath. And the idea here was that since the electric force would be going up and the gravitational force would be going down, if the particle size was just right, such that the Fg would be equal to the Fe, or the electric force would be equal to the gravitational force, this particle could become suspended in between the plates. So we can imagine if the oil drop was too big, the force of gravity would have been bigger, and the electric force would have been smaller, and that particle would have fallen. And if the particle was just right, too small, the electric force would still be pretty big, but the gravitational force would be smaller, and that particle would rise up to the top. And then we had some particles that were just the right size. So what that means is the force of gravity and the electric force acting on them balanced each other out completely, and as a result, the particle was able to stay hanging there in the air in between the two plates. With that in mind, because we can set our voltage and we can separate our plates by how much we want, we can get a very sensitive measurement of the charge of the object. So if the force of gravity acting on this particle is the mass times the gravitational constant, assuming this experiment is taking place on the surface of the Earth, and the electric force acting on the object is the electric field times the charge. And then we remember from a previous video that the electric field is equal to the voltage divided by the distance between the plates. Then we can substitute that in. And we can control the voltage and control the distance, and we know the gravity. So if we can find the mass, then we can use that to find the charge. The charge would be equal to the mass times gravity times the distance between the plates divided by the voltage across the plates. So how can we find the mass of that particle? Well, in this situation, Miliken had a really good way of determining the mass of the particle based on its density and its radius. So by looking at the terminal velocity that particle would have fallen at before the field was there, he could get a very sensitive measurement of the radius, and then using the radius and assuming it was a sphere, he could come up with the volume of the sphere. And then once he had the volume of the sphere, he could use the density. If he had the density and the volume, then he could use that to get the mass of that object, and then he could take that mass and use that to get charge. So that's what he did. It's obviously oversimplified. Coming up with the radius, for example, based on a terminal velocity is more complicated than I'm letting on, but for our purposes, that's our understanding of what he did. What's important about this is that he discovered something strange about all the charges that he found. He found that the charges that he kept measuring tended to be multiples of the same number. So imagine, just to make the math a little bit simpler, you were doing some sort of measurement and you got like 9, 6, 3, 3, 15, 21, and 18. And you looked at all those numbers and you realized they're all multiples of 3. So like this is 3 times it, this is 2 times it, and so on. So what does that mean? Well, what he realized was that electric charge must be coming in some chunk, right? And that chunk could be multiplied by a number of chunks. So one of the oil drops might have had 3 chunks, another oil drop might have had 5 chunks. So with our simple analogy here, this one would have led to a measurement of 9, this one would have led to a measurement of 15 because each chunk size was 3 big. In Miliken's actual experiment, he discovered that this chunk size was 1.6 times 10 to the negative 19 coulombs. And so what he decided was there must be a basic or minimum unit of charge, some sort of discrete amount of charge that everything that has charge is a multiple of. So for example, one electric charge, the elementary charge, is 1.6 times 10 to the negative 19 coulombs, and all charges that are measurable should be some whole number multiple of that. So this can be any whole number. So like 1, 2, 3. So an object can have a charge of 1.6 times 10 to the negative 19, or 3.2 times 10 to the negative 19, or 4.8 times 10 to the negative 19, if n was 1 or 2 or 3 respectively, but it can never have a charge of 2.0 times 10 to the negative 19. It just doesn't come in that step size. It's made up of these blocks, and these blocks have a specific value, so all you can do is get a multiple of those blocks, or a certain number of them. In a sense, this was him observing the electron for the first time, because what we discovered later is that the discrete particle that carries how much charge an object can have is the electron, and all charges that we observe in our normal world are multiples of the number of electrons that have either been removed or added to a system. So that is actually the electron, or how much charge there is on one electron, and this is the number of electrons that are either excess in a charged object or deficit in a charged object. Let's finish off now by going through an example where we look at this whole process step by step, and we'll see what charge we get, and then we'll figure out how many electrons that must have been associated with. So let's say we have an oil drop with a density of 0.837, and it has a radius of, oh, I didn't type that in. Okay, I'm mostly through this video, and I'm gonna just pause here for a second and pick up this calculation in a separate video. I'm running low on battery here, and I don't want to lose what I've done already. So I'm just gonna cut this video off, and like I said, I will do this calculation that I was just about to start in another video that I will do in a few minutes.